Today, we study section 3.7, the chain rule. Take a review about the derivative formulas from these three sections. In these three sections, there are 10 formulas. I divide these 10 formulas into two groups. The first group is for general functions, and the second group is for special functions. Each group has 5 formulas. In group 1, formula number 1 is constant multiple formula. It says that derivative of a constant times a function is the constant times the derivative. We can move the constant outside the derivative. Formula number 2 is summation formula. It says that derivative of a sum is the sum of the two derivatives. Formula number 3 is the difference formula. Difference formula says that derivative of a difference is the difference of the two derivatives. Formula number 4 is product formula. Derivative of a product is the derivative of the first function f times the second function g plus the first function times the derivative of the second function. Formula number 5 is the quotient formula. Derivative of a quotient is the derivative of the top function f times the bottom function g minus the top function times the derivative of the bottom function, then all divided by the square of the bottom function. The second group also has 5 formulas. Formula 1 is for constant functions. Formula 2 is for power functions. Formula 3 is for exponential functions. One special case is derivative of ex is ex. Formula number 4 is for trigonometry functions. And formula number 5 is for logarithmic functions. A special case is derivative of natural log is 1 over x. The 10 formulas allow us to find the derivatives of many functions. However, they are inadequate to find the derivatives of all functions. To find the derivatives of all functions, we need the 10 formulas plus the chain rule. For example, the 10 formulas cannot find the derivatives of this function and this function. We have a formula to compute the derivative of psi of x. But the function here is psi of x plus 1, different. We cannot directly apply this formula to compute the derivative of this function. Mathematics is precise. A little difference may lead to a big difference in the result. Similarly, square root of 1 plus x is a power function. We have a formula to compute the derivative of a power function. But this formula requires the base is x rather than 1 plus x. So we cannot apply this formula to this function. To find the derivative of this function and this function, we need these two formulas plus the chain rule. Here is the chain rule. Suppose we have 3 variables, y, u, and x. If y depends on u, and u in turn depends on x, as a result, y depends on x. So y is a function of x. In mathematics, if something depends on another thing, we say that the thing is a function of another thing. This is a chain of dependence. The variable u is called an intermediate variable. Now, we want to compute the derivative of this function. The formula is dy dx, dy dx, this notation means derivative of this function, is equal to dy du. dy du is the derivative of this function times du dx. du dx is the derivative of this function. This is the chain rule. So chain rule says that the derivative of this composite function is the product of the derivative of this function and the derivative of this function. We can plug in g of x in the u here to get this equation. The chain rule is easy to remember if you view dy, du, and du, dx symbolically as quotients. Since then, canceling du on the right side of this equation, canceling du, then we can get back to the left side. Mathematically, however, dy, du, and du, dx are not quotients. In fact, they are the limits of quotients by definition. dy, du is the limit of this quotient, and du, dx is the limit of this quotient. This formula has only one intermediate variable. In fact, the chain rule can have multiple intermediate variables. The corresponding formula is here. Suppose y depends on u, u depends on w, w depends on v, v depends on s, and s depends on x. As a result, y depends on x. Therefore, y is a function of x. In this chain of dependence, u, w, v, and s, they are intermediate variables. Now, I want to compute the derivative of this composite function. The formula is dy dx is equal to dy du. dy du is the derivative of this function times du dw. du dw is the derivative of this function times dw dv, derivative of this function, times dv ds, derivative of this function times ds dx derivative of this function. This is the chain rule with multiple intermediate variables. This formula is easy to remember. If we cancel du, cancel dv, dw, cancel dv, and ds, then we can get back the left-hand side of this equation. Essentially, this chain rule says that the derivative of this composite function is the product of the derivatives of all these functions. Take a look at some examples about how to use the chain rule to solve problems. Example 1. Differentiate this function by expansion. B, by the chain rule. C, by the chain rule again. Solution to part A. Before computing the derivative, we expand this square. Then this square is this polynomial. Then take derivative. The result is 4x to the third plus 4x. Solution to part B. Find the derivative by the chain rule. In order to use the chain rule, I split the given function into this function and this function. Then I have y depends on u depends on x. If I plug in x squared plus 1 in the u here, then I get back to the given function. So the given function is a composite of this function and this function. Now I compute the derivative on this function by the chain rule. By the chain rule, dx dy is equal to dy du. dy du is derivative on this function. It is 2u times du dx. du dx is the derivative of this function. X squared derivative is 2x. 1 derivative is 0. So I have this equation. Simplify this product a little bit. I have this equation. U is an intermediate variable. Let me plug in x squared plus 1 in the u here. Then I have this equation. Expand this product. Then I have 4x to the third plus 4x. This is the derivative of this function. This result is the same as the result in part A. Solution to part C. Find the derivative by the chain rule again. In this solution, I present a second way to use the chain rule. Take derivative on the function y with respect to x. Because y is this function. Plug in this function in y, then I have this equation. The function x squared plus 1, then the whole thing square is complicated. Let me simplify this function by introducing an intermediate variable, u. I let u below x squared plus 1. then the function becomes very simple, just u square. U square is a power function, so I want to use the formula for power function to compute this derivative. But this formula requires all the variables are the same variable. In this derivative, u and x are two different variables. So I cannot apply this formula to compute this derivative. To overcome the difficulty, I insert du to the bottom and put a du on the top. Essentially, this step is the chain rule. If I cancel du, I can get back here. Now, du square over du, this is derivative on u square with respect to u. This derivative, I can apply this formula here. This derivative is 2u. Then I have this equation. Don't forget, u is x squared plus 1. So I plug in x squared plus 1 in the u here. Then I have this equation. This derivative on x squared plus 1 with respect to x is 2x plus 0. Now, simplify this product, then I have this equation. Plug in x squared plus 1 in the u here, then I have this equation. Expand the product, then the result is 4x to the third plus 4x. This result is the same with the results in part A and in part B. The solution in part B and the solution in part C are both about using the chain rule to compute a derivative. For me, I like the solution in part C because it seems that the way of using the chain rule in part C is easier to explain things in later sections. Here is a guideline to use the product rule, the quotient rule, and the chain rule to compute the derivative of a function. A. When the function is a product, use the product rule. B. When the function is a quotient, use the quotient rule. C. When you want to simplify the function, use the chain rule. Example 2. Differentiate these functions. Part A. Take derivative on the function y with respect to x. Replace y by the function, then I have this equation. Now, I want to simplify the function. I let u be x squared. Then the function becomes e to u. For this derivative, I want to use this formula. Derivative of ex is ex. But this formula requires all the variables are the same variable. In this derivative, u and x are different variables. To overcome the difficulty, I insert du to the denominator and put du on the numerator. This step is chain rule. I can cancel du, and go back here. This is a product of two derivatives. For this derivative, I can apply this formula to get e to u. The variable u is an intermediate variable. It is u is equal to x squared. So I plug in x squared in the u here to get this equation. Now, derivative on x squared with respect to x is 2x. Then move 2x to the front. This is the answer of the derivative of the function in part A. Solution to part B. Take derivative on the function y with respect to x. Replace y by the function. Then I have this equation. The function is a little bit complicated. I simplify the function by introducing an intermediate variable u. I let u be 1 plus x. Then the function becomes square root of u. Square root of u is a power function. It is u to 1/2. So I want to use the formula for power function to compute this derivative. But the formula requires all the variables are the same variable. In this derivative, u and x are different variables. So I cannot directly apply this formula to compute this derivative. To overcome the difficulty, I insert du to the bottom and put du on the top. This step is the chain rule. This is a product of two derivatives. For this derivative on u to 1/2 square root is 1/2. Derivative on u to 1/2 with respect to u. I can apply this formula to it to get 1/2 times square root of u. Why this derivative is 1/2 times square root of u? The detail is here. Now, I remove the intermediate variable u by plugging 1 plus x in u. Then I have this equation. Derivative on x plus 1 with respect to x is 1 plus 0. Derivative of x is 1. Derivative of 1 is 0. So I have this equation. Simplify this expression a little bit, then this is the answer to part B. Part C. Compute the derivative of this function. Take derivative on the function y with respect to x. Replace y by the function. Then I have this equation. The function is a power function. The power is large. I want to simplify this function. So I introduce an intermediate variable, u. I let u be 5x plus 4. Then the function is u to 1000. To compute this derivative, I want to use this formula. But this formula for the power function requires all the variables are the same variable. In this derivative, u and x are different variables. So I cannot directly apply this formula to this derivative. To overcome the difficulty, I use the chain rule. I insert du to the bottom, put a du on the top. This is a product of two derivatives. I can cancel du, and go back here. For this derivative on u to 1000 with respect to u, I apply this formula to get 1000 times u to 999. Now I plug in 5x plus 4 in the u here to remove u. Then I have this equation. For this derivative, 5x plus 4. 5x, the derivative is 5. 4, the derivative is 0. So this derivative is equal to 5. Simplify this expression, then this is the answer to part C. Example 3. Differentiate this function. The power in this function is x times psi of x, not just x. So we cannot directly apply this formula to compute the derivative. Now, take derivative on y with respect to x. Plug in the function in y, then I have this equation. Now, I want to simplify this function. I let u below the power x times psi of x. Then the function becomes very simple, just e to u. To compute this derivative, I want to use this formula. But this formula requires all the variables are the same variable. Here, u and x are different variables. To overcome the difficulty, I use the chain rule. I insert du to the denominator and put a du on the numerator. This is a product of two derivatives. The derivative of e to u with respect to u by this formula is e to u. So I have this equation. Now I remove the intermediate variable u. I plug in x times psi of x in the u. Then I have this equation. Here, I still have one derivative to compute. I compute this derivative here. After I get the result, I put the result back here. The function in this derivative is a product. It is x times psi of x. So to compute this derivative, I use the product formula. By the product formula, this derivative is derivative on the first function. The first function in this product is x times the second function. The second function in this product is psi of x plus the first function times the derivative of the second function. Derivative of x is 1. Derivative of sine is cosine. Then I have this equation. Simplify this expression a little bit. Then this is the result of this derivative. Now I plug in the result here. Then derivative of the given function is this. Example 4. This example has 2 parts. Part 1. Compute the derivative of this function. Part 2. Write down the equation of the tangent line to the curve at the point 3. To help myself answer part 2, I arbitrarily draw a curve and suppose this curve is the graph of the given function. Suppose point 3 is here. Correspondingly, the point on the graph is point P. The x-coordinate of point P is 3. The y-coordinate is function value at the point 3. At this point, there is a tangent line, and we need to write down the equation of this tangent line. Solution to part A. Compute the derivative of this function. This function is complicated, and I want to simplify the function. I let you denote x minus 2 over 2x plus 1. Then the function becomes simple. It is u to the ninth. Now compute this derivative. Because u and x are different, so I use the chain rule here. I insert du to the denominator and put a du on the numerator. This step is the chain rule. This is a product of 2 derivatives. The derivative of u to the ninth with respect to u is 9 times u to the 8th by the formula for power function. Now replace the intermediate variable u by x minus 2 over 2x plus 1. Then I have this equation. In the following, here, I compute this derivative. Because the function in this derivative is a quotient, x minus 2 over 2x plus 1. I use the quotient formula to compute this derivative. By the quotient formula, the derivative is derivative on the top. The top is x minus 2 times the bottom. Bottom is 2x plus 1 minus the top times the derivative of the bottom. Then all divided by the bottom square. X minus 2 derivative is 1. 2x plus 1 derivative is 2. So this is the result of this derivative. Now plug in the result here. Then the derivative of the function g is this. Simplify this expression, then we get the result. This is the derivative of the function g. After we get the derivative of the function, we can tell the slope of this tangent line. Plug in the point 3 into the derivative. Then we can get the slope of the tangent line. The slope of the tangent line is this number. Now, we can write down the equation of the tangent line by the point slope formula. Y minus y1. y1 is the function value at the point 3. How to get the function value at the point 3? Plug in the number 3 in the x here. Then we can get the function value at the point 3. The function value at the point 3 is this number. It's equal to slope, this number, parenthesis x minus x1. x1 is the number 3. So this equation is the equation of the tangent line to the graph of the function at the point 3. Example 5. Find the derivative of function f, where function f is sine of cosine of tangent. Please note that this function is not a product, not sine times cosine times tangent, but it is a composite function. For example, if you want to compute the function value at 1, then you need to first compute tangent of 1. Tangent of 1 is this number. Then compute cosine of this number. Cosine of this number is this number. Then sine of this number. This is the function value at the point 1. Now, take derivative on the function f. The function is quite complicated. To simplify the function, I denote cosine of tangent of x by u. Then the function is reduced to sine of u. To compute this derivative, I want to use this formula. Derivative of sine is cosine. But this formula requires all the variables are the same variable. Here, u and x different. So I need chain rule. I insert du in the denominator and put du on the numerator. This step is chain rule, and this is a product of two derivatives. Now, derivative of sine of u with respect to u, I can apply this formula. Then I have this equation. Now remove the intermediate variable u. U is cosine of tangent of x. So plug in cosine of tangent of x in the u here. Then I have this equation. Now, next, I need to compute this derivative. The function in this derivative is not a product. It is not cosine times tangent. So we cannot use the product formula to compute this derivative. The function in this derivative is cosine of tangent, a composite function. To compute this derivative, we need the chain rule. Now, I simplify the function by denoting tangent of x by w. Then the function becomes cosine of w. To compute this derivative, chain rule. I insert dw in the denominator. To cancel this dw, I need to put a dw on the numerator. This step is the chain rule, and this is a product of two derivatives. Derivative of cosine of w with respect to w is negative sine of w. Now, w is tangent of x. Plug in tangent of x in w here. Then I have this equation. Derivative of tangent of x with respect to x by formula is secant squared. So this is the result of this derivative. Plug in the result here, then the derivative of the function f is this. In this solution, I have used the chain rule twice. I use the chain rule here. When I compare this derivative, I use the chain rule again. So I use the chain rule twice to get the solution in this example. Recall that the chain rule has two formulas. One is with only one intermediate variable. The formula is here. The second one is with multiple intermediate variables. Take a review about the formula with multiple intermediate variables. Suppose y depends on u. U depends on w. W depends on v. V depends on s. And s depends on x. As a result, y depends on x. Therefore, y is a function of x. Now, the formula to compute the derivative of this function is dy dx is equal to dy du. Dy du is the derivative of this function times du dw, derivative of this function, times dw dv, derivative of this function, times dv ds, derivative of this function, times ds dx, derivative of this function. This is the chain rule with multiple intermediate variables. This formula is easy to remember. If we cancel du, cancel dw, cancel dv, cancel ds, then we can get back to the left side here. The chain rule, this chain rule, says that the derivative of this function is equal to the product of the derivative of all these functions. Now, move back to example 5. I have presented one solution to this example. Actually, this example has a second solution. In the second solution, I use the chain rule with multiple intermediate variables to solve the problem. In order to use the formula, I split the given function into several simple functions. I split the given function into y is sine of u. U is cosine of w, and w is tangent of x. If I plug in tangent of x in the w here, then I have cosine of tangent of x. Plug in cosine of tangent of x in the u here, then y is this function. Now, by the chain rule with multiple intermediate variables, the derivative of this function is equal to the product of the derivatives of all these three functions. The derivative of sine of u is cosine of u. The derivative of cosine of w is negative sine of w. Derivative of tangent of x is secant square x. Move the negative sign in the front, then I have this equation. Now, delete the intermediate variables. U is equal to cosine of w. I plug in cosine of w in the u here. Then I have this equation. Now, delete w. W is tangent of x. Plug in tangent of x in the w here. Then I have this equation. This is the result of derivative of this function.